Okay. Well, reviewing where we were at. Now we are going to have a quiz over here on the board. I got a couple of things. We are going to have a quiz on Wednesday. Now that's our day that's scheduled for next Wednesday's on the backboard there. It's kind of like the 2-hour late start. Except it's reversed. We have 3 blocks before lunch, and they're about the same length. Lunch will happen at the same exact time, 11 to 12:20, with block 4 being after. So it's an hour, about 55 minutes. So I'll try to adjust the quiz. I'll make the quiz, in such a way that that will be an appropriate amount of time to be able to get it done. And that's. It's just better not to carry over. Typically, I want to do one other section. A lot of times I'll do one other section before we quiz on this stuff, but then that kind of carries it over to Thanksgiving break, and that's probably not the best scenario. So we'll go ahead and do a quiz next Wednesday. Is anybody going to be gone that day?
Not the day before Thanksgiving.
The day before Thanksgiving.
I may or may not. Okay, brother. Depends on if you can get married.
Okay, so the best case would be to do that before, like a Tuesday, after school or something, as opposed to waiting until the next Monday, because that's probably when you would need to do it, after break. So be thinking about that. So that's next Wednesday. And also on the board then I have this definition that we have, which is the definition of derivative. So if we want to kind of review where we came from. So what I said, average rate of change, I mentioned yesterday, that's an algebra concept, slope between 2 points, slope of the secant line. You could write it like this, or you could write it like this. The bottom line is just 2 points, right? You could write it y2 minus y1, but f of b minus f of a. But yesterday we said let's call the first point a, and let's call the second point a plus h, because so a is like the left-hand point, and then move over h units, and then that's your second point, a plus h. And so these are the same thing. These two are just different notation, right? And then the run is the h, right? So it's rise over run. So when we get to calculus, then we want to do instantaneous rate of change, which is the slope at 1 point, which is the slope of the tangent line. And then what we do is we just take the slope between the 2 points, and then we make the 2 points become 1 by letting h approach 0. All right, so here's the picture we had yesterday. So this is just a picture of the 2 points becoming 1. But if you want to open to your notes here real quick, I've got something here that wouldn't be a bad thing for you to write down in your notes. So this is the picture. You may have drawn this in your notes yesterday, but this is just a picture of how we would get the slope at this 1 point right here. Is we would let the slope between these 2 points, here slowly become that tangent line. And I did that thing where I dragged the line, and you could see it do it, right? So that's what we have right there. Okay? So what I wanted to show you was this picture. Okay? This is kind of an alternate version. So if you want to write that at the top of this is just kind of an alternate version that you sometimes see of the definition of the derivative. And notice the difference. It's just how we label the points. We still have 2 points. We're still doing the slope between 2 points and letting the 2 points become 1. The only difference is we let the first point be a. Well, that's actually the same as the other picture. And then we let the second point, we call that x, right? That's all the difference. So then the y value here would be f of a, the y value here would be f of x. And when we do our slope, we just subtract the y's, f of x minus f of a, and subtract the x's, that'd be x minus a. But then look at the limit. The limit's different then. Instead of approaching 0, we're saying let x approach a. So you're letting this point approach that point, right? In the other one, h was the distance between the points, so we let h go to 0, right? So this would change. So if you were doing f prime of 3, then you'd be having x would approach 3. If you were doing f prime of 4, x would be approaching 4, right? And so it would look a little different. So it's just an alternate version, but it's still the same thing. It's still slope between 2 points, and the 2 points become 1. Okay? So we may run into that from time to time, so I just want you to see it. But this is the one you're really going to use. This is the one we'll refer to all year long. Okay? The one we talked about yesterday. All right? Okay, so here's an example. This is very similar to the one that we did in class yesterday. So over here, I may put these notes up under the assignment today, just kind of so you got some place to look. You got your own notes, obviously. You got the definition of derivative. I went through the whole thing here. I decided to use a peanut instead of a German short hair, because I thought that'd be fun. Okay, Connor, give me your calculator. You're gonna go out in the hall there. So you have to check in. Go back to this. All right. So this was just an example one, and so yeah, f of 1 it would be this, f of 5 would be this, f of z means put a z in for the x, f of peanut means put a peanut in for the x, f of 2 plus h means put a 2 plus h for the x. So I used a little bit of color here to kind of differentiate. So we always start by doing this. We always want to start here by doing the definition, that thing in red up here. So I always like putting, no matter what the function is, if it's sine or e to the x or log or whatever, it doesn't matter what the function is up here, I always want to start by writing it there. I call that the F notation. Start by writing it out in F notation. Okay? Just mimic this. In other words, put your 2 in place of the A. Start with that. Then you can say to yourself, okay, the blue thing, what's f of 2 plus h? Oh, that means plug a 2 plus h in for x. So we plug that there, we plug that there, and it gives us the blue thing. And then we got to plug a 2 in for x. So we plug a 2 in for x, and that gives us the a. When we do all the algebra to it, nice things should happen. Things should cancel, that should cancel with that and that. We end up with this. We can factor out an h. Those cancel. Then, what's the beauty of the h canceling? Then you can put a 0 in for h. And what does the 0 in for h do? Well, yeah, it makes h be 0, but what's it do? The 2 points become 1 point, right? It allows it to be the tangent line. It allows it to be the slope at that 1 point. The h being 0 allows the 2 points to become 1, and so we get the slope at that 1 point, the instantaneous rate of change. But we can't put a 0 in for h up here because we've been divided by 0. And we can't put a 0 in for h here or here or here. But once we get that h to get out of there, then we can let the h be 0, and then we see that the slope is 6 in that particular problem. Here's the other one we did yesterday, the same scenario. This is the one where we got the 70. This is what your work looks like when you do the definition of the derivative. Okay, to the homework. Were there any questions on this one where you had to do the thing with the stock prices? Now, I know you guys have been looking at the answer book, taking pictures of it, going home, whatever. I get it, but remember, I had several people in here this morning asking about stuff. They said, well, the book had this, and I just went with it. I just wrote it down, but I didn't know what they were doing, right? That's where you got to be honest with yourself and not just be satisfied with getting an answer down. I mean, that's what it looked like on some of your papers. So, and make sure you know where that's coming from, and you can do it yourself. So any questions here? Well, bottom line was they asked you about average rate of change. What's average rate of change? Slope between 2 points. So you just do the slope, so you'd subtract dollars, and then on the bottom it'd be what, hours? Right, so it'd be dollars per hour. Instantaneous rate of change. How are you going to do the instantaneous rate of change at 9:15? You're going to draw a tangent line, and you're going to do rise over run. Like that, right? I mean, we can't forget the stuff we learned before it. We cannot do, I was talking to somebody that came in this morning, they were trying to use this for the instantaneous rate of change. Why can't you do that? Well, we don't have an equation to plug it into, right? I mean, if you want to do the instantaneous rate of change at 9:15, so you want to plug a 9, what would that be, 9.25, 9 1/4? You want to plug 9.25 in for your A, fine, but what do you plug it into? There's nothing to plug it into. right? There's no equation to plug it into like we had back here, right? So if you don't have an equation, you're not going to be able to use this thing over here, right? So sometimes we still have to just do what we learned before. We just draw a tangent line and we estimate the slope. That's it, okay? Especially when the problem said estimate, okay? What problem was this one? For some reason, I wrote this one down. Was this number 4? No. That isn't any. Is that one of the problems?
It's 13.
Well, but it's 13. 13 was one. It's like 13. Yeah, they give you an H. Compute. This is just like zooming, right? So I guess what I did, I wrote this up. I got this slide from last year, and I looked at it. I thought, where the heck was I doing this?
Oh, 35.
It's not 5 either. No, I guess maybe nobody asked about third, but this would be what it would be doing, right? If they say let H be 0.01, they're like saying let H get close to 0, which of course is what this is doing. Let H get close to 0, which is what we did in the last chapter, zooming, numerically zooming. We just pick a really close point, so 2 and 2.01, and so you just work that out. Okay, and I got that. It's 7. Yeah, but it's not even 7 because I got x squared plus 2x, and that's x squared plus x, and so it's weird. Okay, anyway, doesn't matter. Doesn't matter. All right, 43. So I'm going to look at some of those. Now, I know some of you have a question about 34 and 35, right? A lot of you had those blank, weren't sure what to do on that one. And so we will talk about that. But let's go through 41 through 44. So on 43, x cubed. Now, let me see. Okay. All right, so on 43, we've got limit, so we're supposed to find what? F prime of what? 4 on these, okay? So let's go through this. I just think it's worth, and maybe if we're wasting our time here, you got this down cold, I apologize, but I'm just not sure that's probably the case exactly. So the first time you write it, I want you to write what? What'd I say? F of 4 plus H minus F of 4. It would really be nice if you just get so automatic at writing that down. You know that definition so well, you can just, boom, you can just write it right down. F prime of 4, we're going to write this. Now we look at our function, which is x cubed. I don't even care what the function is. You're going to have this line. You should have this line for every one of those problems, 41, 42, 43, 44. You should have that line right there because you're finding F prime of 4 on all of them, right? Just doesn't matter what the function is, all right? So now we look at the function. So now, limit as h goes to 0. What's 4 plus h cubed? Well, that'd be this right here, right? 4 plus h cubed minus, what's 4 cubed? 64. All over h. Okay, now I'm going to break my own rule here just because of time, and I'm not going to write that limit down. So how do I do 4 plus h cubed? Foil and do it again. Now I'm going to give you a little bit of a trick here. Calculator to do it, yeah. Well, guess what? On our next quiz, this will be on the no calculator part, right? So you're going to have to do it without it. But you're right, the calculator does do it. It's the expand command. You go under algebra to expand. You go 4 plus h cubed, expand, it'll do it. Let me show you a little trick. And Mrs. Payne may have shown this. Did you guys ever look at Pascal's triangle? You remember this last year? Huh? Just barely, right? That didn't do a whole lot with it. Pascal's triangle is a really cool thing. It'll do a lot of different things, but one of the things, and what it is 1 plus 1 makes 2, right? 1 and 2 makes 3, 1 and 2 makes 3, 1 and 3 makes 4, 3 and 3 makes 6. That's how you do each row, right? You look at the ones above it, and they're offset, and you can go on and on and on. Okay, well, here's one of the really cool things that Pascal's triangle does. It gives you the coefficients on a binomial expansion. Okay, what do I mean by binomial expansion? Well, if I had x plus y to the 0 power, of course, that's just 1, right? And if I had x plus y to the first power, that's just 1x plus 1y, 1x plus 1y. If I have x plus y to the second power, that's 1x squared plus 2xy plus 1y squared. 1, 2, 1, 1, 2, 1. And if I have x plus y cubed, then that would end up being, watch this now, 1x squared, 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. If I know Pascal's triangle, I can do an expansion of any power by just throwing in those coefficients from Pascal's triangle. And then notice the pattern. This thing started out cubed, then it was squared, then it was first, and then it was none of them. And then the y's went the other way. Y started out with none of them, then 1y, then y squared, then y cubed. See what I'm saying? So I could do this with this. Now, I'm not saying you have to do this. You can do what Will said, right? You can do that. But what if you had 4 plus h to the 6th? That would be a lot of fun, right? I'm probably not going to make you do 4 plus h to the 6th, so you don't have to worry about it, right? But knowing this is kind of cool. So what is this going to be? It's going to be 4 cubed plus a 1 there from here. Then there's going to be a 3, and then it's going to be 4 squared, and then an h, and then it's going to be another 3 from Pascal's triangle, then a 4 to the first, and then an h squared, and then it's finally going to be a 1, and then a h cubed. See what I did? So it's like my x was my 4 and my h was my y. So I did this cube, then it was going to be this squared, then it was going to be this to the first, then it's going to be none of those. And then this will be none of those, then an h squared, then an h cubed. And then I also had the 1, 3, 3, and the 1 from Pascal's triangle. So what do you end up with here? You end up with 4 cubed, which is 64. You end up with 16 times 3 is 48h. You end up with 4 times 3 is 12h squared plus h cubed. Right? Did I do that right? Is that what you guys had? Okay? Right? So with Pascal's triangle, boom, 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 you can do that. It's pretty quick. Now, that might not have been a lot faster than just foiling it out, but whatever. So take away 64, all over h. Okay, let me get rid of this. All right, so we go there. The 64s cancel, like we said. We end up with, we can take out an h, can't we? So we can take out an h. We end up with 48 plus 12h plus h squared all over h. The h's cancel. Now we can let h go to 0. When h goes to 0, what do we get? 48, right? Because this will go away and this will go away, right? There you go. Okay? So, again, you're going to need to be able to do this without a calculator. All right? So what did we just find there? Don't forget. Don't lose sight of what you were doing there. We just found what? Slope at, that's a really steep slope, 48. Does that make sense? It'd be that steep? Slope of 48. Why? Why does that make sense? What's that skew do? I mean, it's going way straight up. By the time you get way out of 4, that graph is really going up high. Okay? So it makes sense. All right, let's stop here a minute before. I want to talk about 44 now. I want to talk about 34 and 35. But let's stop here and talk just a minute about this right here. Okay, and you can jot this on scratch paper in your notes, wherever on your homework paper, I don't care. But if I give you this function right here, and you had your calculators, okay, you had your calculators to use, how many different ways could you find or estimate f prime at 1 right now with everything we know? Take a few minutes to think about it. Just jot down some things you could do. How many you got? How many? 3? Have we got more than 3? What's 1? The definition, the thing we just learned. Okay? So we can work out that long way. Right? Okay? What else? Graph it, sketch a tangent line. Okay? What's another one? Zoom in. 1 and 1.001, right? Do a slope calculation there. Okay? All right. I would agree. Any other one would probably just be variations off of that, I suppose, right? So those are the different ways, depending, and that's what, like I was saying to you before. I know it's not an issue. Hey, Connor, I know it's not an issue, but leave your phone. I trust you completely. So that's it. Now, what our goal today is to add one to this list. Okay, to add one to this list. That would be, now, what's the problem with these two? Well, say that again. Yeah, you have to have a graph, so you need your graphic calculator or whatever. If you didn't have a graphic calculator, or if it's no calculator, that'd be difficult. And then what was the other, what did you say? They're estimates, right? They both be estimating, right? Now, your calculator has the capability to just give us this answer also. I mean, just tell us the answer, right? And we haven't learned that yet, but it does have that capability. So that'd be another option once we learn that. Of course, the downside of that is most of the time we're going to have to be able to do this without a calculator, right? So that's so that'd be another one we could do. And then what's the downside of this one? It's long. Yeah, it's long. I mean, other classes we've called this the long way. Of course, to you it's the only way right now, but by the end of today, you're going to recognize, oh yeah, that's the long way. There's shorter ways we can do it. Okay, but it's important because the definition. I never want you to lose sight of the fact that what we're going to learn today, these kind of shortcuts, are that they all come from this. That they come from slope. The derivative of slope. I never want you to lose sight of that. It's important that we understand where they come from. All right, so let's talk about some notation. Okay, so let's talk about some notation here. So this would be for your notes now. We're kind of bouncing, I know, back and forth between your notes and your homework. But so this is some notation for derivative. Okay, now the notation we've used up until now has been pretty much just this here in the blue, right? If f of x is sine x, and of course this is one we learned, right? We showed it again yesterday. If f of x is sine x, then f prime of x is cosine x, right? And so we talked about that. And of course we know e to the x is its own derivative, right? If f is e to the x and f prime is e to the x, remember when we did that? The y values and the slopes are the same. Okay, but now I want you to get used to this notation over here too. We sometimes will just use y instead of f of x. We don't a lot. We've been using function notation more. So you might get a y and a y prime, right, instead of f and f prime. Same thing. But now I want you to really look at this notation here because you're going to start seeing this notation more and more. And this is called Leibniz notation. I'm not sure if I spelled that right. I don't know if it's e before I or I before e, but for some reason that didn't look quite right. Leibniz notation. Yeah, it's e before I. Leibniz. Okay, Gottfried Wilhelm von Leibniz, who is, along with Isaac Newton, were kind of the co-inventors of the ideas that kind of eventually came together to be calculus. So this is his notation for the derivative, dy over dx. Now, a couple of things about that notation. It comes from slope, because this means this is delta y over delta x, the Greek letter delta. It looks like a triangle. Greek letter delta stands for change in y over change in x, which of course is what slope is. Change in y over change in x. So we use d's instead of the triangles, but that means slope. Now it's not a division, we're not dividing anything, it's just dy over dx. A lot of times we just say dy dx, right? But what we really mean is dy over dx, right? But a lot of times we'll say dy dx, okay? But it's dy over dx, okay? The way you want to read this is derivative of y with respect to x. Think of the bottom as just being with respect to. It's telling you what the input variable is. The downside of the y prime notation, we don't really know what the input notation is, and we could have written that y of x or whatever. But this tells you the input variable. That will become important sometimes. So we'll sometimes see that notation. Okay, now the one real advantage to Leibniz notation then you see over here on the right. Because so dy dx is the same as y prime. That's the same as writing y prime. So when you see dy over dx, when you see dy over dx, that means derivative of y with respect to x. So it's y prime. It's y prime. So dy dx is the same as y prime. They're just exactly the same. They're just two different ways of saying it. Okay? But what the nice thing about it, think about this. You know how in a fraction, if you have 2x over 3, you know how you can move that x and just stick it down in front like that, and it's the same thing, right? So 2x over 3 is the same as 2/3 x, right? Everybody agree with that? So if it's on top, it's kind of like being out in front, same thing. Well, we can do that same thing with this notation. We can take the y out of here, which in this case the y is sine. We can take the y out of the top and just stick it out in front. So what's nice about this is we can say both of those in one line. Instead of saying y equals sine, y prime equals cosine, we can say the derivative of sine with respect to x is cosine. So that's what that line is saying. So from here on out, we're going to use this a lot. Because what we're going to learn today are some derivative rules. And this allows us to say it in one line instead of two lines like we need here. So we can just say the derivative of sine is cosine. So that's your y. And then, of course, then this is your y prime over here. Or your f and your f prime. Okay? So don't think this doesn't mean sine x divided by x, right? That's not what it's saying. It's just saying the derivative of sine with respect to x is equal to cosine. Okay? And I usually won't say the with respect to x. I'll usually just say derivative of sine is cosine. That's what we'll say. And so derivative of e to the x is what? E to the x, right? It's its own derivative. Derivative of e to the x is e to the x. Okay. Now, second derivative. How do we say second derivative? Well, we've already talked about f double prime. Of course, you could say y double prime. And then in Leibniz notation, this is second derivative. It's not squared. That doesn't mean squared, even though it looks like it's an exponent. It isn't an exponent, but all it means is second derivative. So that's Leibniz notation, means second derivative. Okay, that's all it means. It means y double prime. Okay, what's it come from? It comes from this notation. It's like saying the derivative of the derivative. If you think about it, the derivative of the derivative. If you look at that, that kind of looks like d squared y and then dx squared. Now you might say, oh, you need parentheses. Yeah, but you see where it comes from? The derivative of the derivative. Second derivative. So that's kind of where that notation comes from. Okay? All right, so just a matter of knowing the notation. It's not hard. It just means y prime. It's just another way to write y prime. And then, of course, this means the derivative of the thing in the brackets equals that. All right, let's go back to 44. This is one we've got to be able to do. This is an algebra. If you were in Mrs. Payne's class, you know she talked about bow tie. This is getting a common denominator. You've got to be able to do this. We will do some practice between now and next Wednesday of just some algebra ones where you do this. But I've already started it out here, so let's go through it because I'm guessing some of you got an answer here maybe from the back or something or from the answer book, but I'm not sure you knew what you were doing. So what do we get when we plug in a 4 plus h? Right? Minus, then we plug in a 4. 2 over 4 or 1/2, right? So you can write 2 over 4, but if you'd rather just go write the 1/2, you can do that. Now it's going to look different depending on which one you do, so I'll go ahead and do 1/2. And then the bottom is 8. So it doesn't look so bad, too bad so far. Problem is, what we know we need to do is cancel out that h, right? We want to do some algebra. The other ones were easy, those power ones. We just factored them out, or we just expanded them out, canceled things. Yeah, everything worked out wonderfully, okay? But now we're sitting here going, well, what do? Well, you got to get a common denominator. So I'll just ask you, how do you do 1/2 plus 1/3?
36 plus.
You got to get a common denominator, right?
Well, what if you split up the first part to 2 over 4 and plus 2 over h?
If you did that, you would be violating so many different rules that we would have to kick you out of the calculus. Okay, let's talk about that. I'm glad you said that. The other day I talked about splitting up a fraction, right? This fraction I can split up into 2/7. That's right. If I switch this around, okay, and let's just see this. See, so everybody agrees this is 5/7 either way you do it, right? Now this is 7/5 clearly, right? We all agree this is 7/5, right? Which is what, 1.4, right? If I split this apart, this would be 7/2, which is 3.5, plus 7/3, which is 2 1/3, which is definitely not 7/5, right? Which is 1.4. This is definitely way more than that. Okay, so what's the lesson? The lesson is if you have a single denominator, you can split it apart, right? But you never split a denominator, right? With plus signs especially, okay? Now, if I had 3/2h, could I split that into 3/2 times 1/h? Now that's different because with times you just multiply the top, multiply the bottom, right? So with times it's a whole different story. But with plus we can't do that. Okay, so important lesson, and that is an important lesson I have to repeat every year, and that's fine. And so I'm actually glad you said that. So now back to this. What's 1/3, 1/2 plus 1/3? We got two ways to do it. You can just get a common denominator so you can understand right away that the common denominator is going to be 6. So you're going to have to take, I hate it when it does this. Thank you. So you realize that the common denominator is going to be 6, so you need to multiply these like that, right? A fancy one, right? And you turn that into 3/6, and you turn that into 2/6, and then you add them together, okay? So what that means, to do that, you have to realize what's my common denominator between these two here. And that's where it gets a little tricky for some people. So Mrs. Payne teaches a method, which is not bad. The other thing you can do when you have a fraction like this that you want to add up is called the bow tie method. And what you do is you multiply those. Now, I hate to call this cross multiply because it really isn't cross multiply. Cross multiplying is with proportions, which is something different, but it's kind of the same thing. So what you can do is you can multiply there and get this, right? Then you can multiply here and get this, and then what goes on the bottom? You go across the bottom, and she called that a bow tie, right? And 2 times 3 is 6, like that. So you start up here in the upper left. That's key. You got to start up here in the upper left, because if there's a minus sign like there is here, that's going to matter. So you start up here in the upper left, and you go down here. That's 2. Then you start in the upper right, and you go down here, and that's 3. Those go on top, and then you circle the bottom, and you multiply those. And then that goes on the bottom. And then that's 5/6. So if we're going to bow tie this, we're going to start up here. 2 times 2 is 4. Then we got a minus. Then we're going to start up here. We have 4 plus h. You've got to remember to put that in parentheses because of that minus sign. Okay, so we're going to go here to here, which is 4. Then we're going to go here to here, which is 4 plus h. We're going to minus those. And then what goes on the bottom? You circle the bottom. 2 times 4 plus h, which of course you can just do in your head. That's 8 plus 2h, whatever, right? That's what you do. Now that probably looks different than what the back. Now don't forget there's an h underneath all that. There's an h underneath all that. Okay? All right, now what? Let me come over here. So now we want to do the top. So we get 4 minus h. The bottom, if you want to multiply it out, you can. That's 8 plus 2h. Now, what happens with this h on the bottom? Well, not the very top. Here's what it does. You're dividing by h. Dividing by h is the same as what? Multiplying by 1 over h. Or another way to think about it is you're going to do this. Right? I like to just say invert and multiply. So when you're dividing by h, you invert it and multiply. Okay? So whatever. It doesn't matter if you think of it this way or you just think, okay, I'm going to bring this h and I'm going to bring it up like that. I'm going to invert and multiply. So actually that h ends up being on the bottom, right, of the top. It doesn't go all the way up to the top here. Okay? It's important you understand. So what happens is that h ends up down here. See, that h ends up down here with that part. Okay? All right. So then, let me go back to my blue. So now, we don't want to distribute that through there because we're going to end up wanting to factor back out anyway. The 4's cancel. So we end up with negative h. This is the part that I'll bet if we have one like this on the quiz, I'll bet there'll be a bunch of people that will forget that negative because you're going to not put parentheses right here and you're going to cancel those 4's, but then you're going to have a positive h sitting there instead of a negative h. So you got to be really careful. Okay? And then 8 plus 2h all over h, and now those h's cancel. And you end up with negative 1 over 8 plus 2h. Now, the beauty of that is, what does that allow us to do now? Do I? Put a 0 in for h, right? Just like the ones we were doing earlier. We can now put a 0 for h. The reason this one looks different is different algebra. It's just different algebra. Here we had just foiling, right? We just had foiling, right? Algebra, because it was powers. This is different algebra. This is getting a common denominator, but it's still just algebra. Okay, we got to be able to do it. Now we can put a 0 in for h, because before, if we put a 0 in for h, we'd still be dividing by 0 down here. But now that the h is canceled, we put a 0 in for 8, and look what we get, negative 1/8. Now, does that make sense? Well, it makes perfect sense, because you know what the graph of 2 over x looks like? It looks like this. And it looks like this. And out here at 4, the slope is about like that. It's negative, but it's not very much. Negative 1. Okay? All right. So, let's talk about some different, before we do 34 and 35, let's talk about some different algebra things here. So, here's just a couple of algebra ideas. The one more algebra thing we need to do. There's 3 algebra things you have to be able to do. Okay? The first one, of course, is the FOIL. I just call it FOIL, but the expanding out the powers, right? FOIL out and cancel and stuff like that. You have to be able to do a common denominator, which is the bow tie thing we just did. And you got to multiply by a conjugate. Conjugate is a plus b times a minus b, which of course just is a squared minus b squared. Okay, you got to be able to multiply by a conjugate. Now, where do you want to do that? Well, you want to do it with radicals typically. So here's a problem right here. Okay, so we're going to run into, this is just an algebra problem, we're going to run into some problems using the definition of the derivative, okay, where we have to do this method, okay? And so here's an example. So right here, the strategy on this one, so think back to Algebra 2 class, and the rule you had was you didn't want the radical to be on the bottom. Now, we're not doing it because we don't want the radical on the bottom. We're doing it because we're trying to get something to cancel. We're trying to get something to happen. But you don't want the radical on the bottom, so what you do is you multiply by radical x plus 2. It's called the conjugate. That's called the conjugate. Okay? So what you have now is a FOIL here down on the bottom. You have an a plus b, a minus b situation. Well, the nice thing about that, when you FOIL that, the outers and inners cancel out. And you get a squared minus b squared. So the top is simply going to be 3 radical x plus 2. To be honest, I usually do not distribute that out because I'm hoping maybe something will cancel. But you can distribute it, but then you might end up having to just take the 3 right back out again, right? And then what's the bottom end up equal?
X minus 4.
And see that? The radical is now not in the bottom end. Now, that's all of that accomplished. What's going to happen in the problems we do is when we do that, some things will then cancel somehow and nice things will happen. Okay? But so when you get one with a radical plus something, or a radical minus something, you're going to want to multiply by a conjugate, because look why the radical disappears, because you multiply it by itself, you square it. So you take the square root and you square it, and the radical disappears, and so nice things will happen. That's called multiplying by a conjugate. Okay, now here's another common denominator one, so let's practice. You guys practice that real quick. Do a bow tie on that. Do a bow tie on that like we just talked about. Okay, do a bow tie on that and see if you can do it. Now see, I just didn't record it. Okay, top, 3 times y, start up here, go down, 2 times x, and then circle the bottom, xy. Okay, now what about that x squared? What I just usually do is I just think invert multiply. Invert multiply. Whatever's on the bottom. If you had a fraction down here, you might have a fraction over a fraction. If there was a whole fraction down here, you would invert that whole fraction. Right? But we're just going to put that up there like that. So what do we get? We get 3y minus 2x over what? X cubed y. Now, it turns out there's nothing more to do, right? We can't factor anything, cancel anything. In our problem, something will probably happen. What we've accomplished, though, we don't have, in algebra, they call those a complex fraction. When you have a fraction inside of a fraction. We don't like that. So what we did is we took this fraction inside of a fraction and we just turned it into a single fraction. So that's considered more simplified, right? But in the process of doing that, when we do them, what's going to happen is you're going to have something nice will happen. Something on top will probably be able to factor out, cancel an h, right? We'll probably be able to factor out, cancel on the bottom, and then you'll be able to put a 0 for h. That's what's going to happen. Okay? So that's how those all work, right? Bow tie gives you the top, you get this thing on the bottom, you're going to flip, it's usually going to be an h on the bottom, isn't it, with our definition? You're going to have an h down there, flip it up, something should change. Okay? All right, you got to be able to do those 3 things. FOIL out things, do a common denominator, get the conjugate. Okay, last problems, and then we'll get into the new stuff. So 34 and 35. 34 and 35 are simply going backwards. Now, first of all, I want to do this. 34, I'm going to take this delta x out of here, and I'm going to replace it with an h. It's the same thing. Delta x is just change in x, and if you think about it, that's all that h is. That's all that h is. H is from a to a plus h. It's just your change in x. Okay, they use delta x, but it's the same as h. Now, what did they say? They said, look at this limit. This limit is f prime of some a, right? And they want you to identify what the original function was and what the a value is. Okay? Well, I say, so here's what they're doing. They're just taking the problems we've done and worked backwards. They've said, okay, here's a limit problem. We're going to do some worksheets to help with this over the next several days, too. But here's a limit problem. And it has this special look to it. Now, how do we know it's got the special look? Well, first of all, it's got h approaching 0. It's got an h on the bottom. And it's got an a plus h. Now, remember the German shorthand, right? The German shorthand, the a plus h gets plugged in where? For the x, right? The a plus h gets plugged in for the x. And also the a gets plugged in for the x, right? Okay, so looking at that problem, can you tell me what this a must be in that problem? Does it have to be 9? Sure it does. It has to be 9. Okay? It just looks, I mean, you just look at those two. Yes, the a had to be 9. Okay? And what was the function? Well, if the a is 9, then we just said the a plus h got plugged in where the x was. Well, where do you, 9 plus h then had to have gotten plugged in where the x was. So what was the function? Square root of x. X to the 1/2. The function had to be square root of x. Now let's finish this out. So what we'd have done is so the first part of this, we'd have put 9 plus h and put it into the x. That would have given us square root of 9 plus h. The second part of this then would have been to take the 9 and put it in for the x, right? What's square root of 9? Well, 3. Oh, that's where that 3 came from. Now this would have been even easier to see if they would have written it this way for us. If they wouldn't have simplified that for us, if they would have just written this, if they just would have written this square root of 9, that would have been even easier to see, right? We'd have seen the a plus h and then the a. We'd have seen a plus h and then the a. We'd have seen square root and square root. We'd have said that's our function, right? But I think you just look at the a plus h part. That gives it away. When you see 2 plus h, 3 plus h, 4 plus h, that gives away the function. It gives away the a too, right? It gives away the a. And it gives away, because the a plus h got plugged in where the x was, so it gives away the function. Matter of fact, if you go back to the ones we did here, look at this. This line right here gives away the function. Because see the 2 plus h, right? That tells me that the 2 must have been the a, right? 2 must have been this number. And then the 2 plus h is where the x was, right? So this function had to have been 10x. Now it turns out it was t, but it doesn't really matter, right? This function had to be 10x plus 15x squared. You see what I mean? This line right here gives away the function. 10x plus 15x squared had to be. And sure enough it was. So it's just working it in reverse is all it's doing. Okay, look at this one. 2 plus h gives it away. The 2 must have been the a, and then the 2 plus h is where the x was. So this must have been x squared plus 2x. Sure enough, there it is, right? That's all they were asking for. Now, forget the stuff about the graphing part. I don't care about that. We're going to do that later. So they said something about graphing the thing, so let's don't do it. Okay, so what about this one? So that's all they want. That's all they really want you to do. So this, if you were to work this problem out, it would give you the derivative of the square root graph at 9. It would give you the derivative of the square root graph at 9, because that's what this is the derivative, right? Okay, what about this one? What is the a? Well, remember, the a is given away. You look for that. The 2 plus h, the 3 plus h, the 4 plus h. Where do you see it here? Sure it is. It's right here. You can't see that. You don't see that there? 0 plus h. What's the a? 0. Yeah. It doesn't have to be 2 plus h or 3 plus h or 4 plus h. It'd be 0 plus h, right? If they'd have written 0 plus h, it would have made it easier for us, right? But there it is. 0 plus h. And then what should this one have been then? And what's the function then? The 0 plus h is where the x was. The function's cosine of x, right? The function's cosine of x. So we put a 0 plus h in where the x was. So the cosine 0 plus h. Now, what's this one supposed to be then? Cosine of 0. What's cosine of 0? 1. Oh, okay. So it would have been easier if they would have written it as cosine 0 here, right? Then it would have been easier to see. And if they'd written it cosine 0 plus h, it would have been easier to see. But we just had to fill that in ourselves. Okay? All right. So this would be, so if you were to work this out, right? And we don't know how we would with that cosine. That's a whole other ballgame. But if we were to work this out, it would give us the derivative of the cosine graph, the slope of the cosine graph at 0. Okay? So it's just thinking about that definition in reverse. Okay. Now, in your notes, here we go. Here's the new element to this. It's not much new. It's just a little bit of extension. But man, is it powerful. It really gives us something that's pretty cool. And some of you have probably already seen it. You know, Will, you were hinting at it yesterday, and I don't know if that's what you were talking about. But we're going to see here in a minute. Okay, so now you don't need to write down this picture, but does this picture look familiar? Does this look like the picture we had yesterday? What's different about this picture? That's all the same, right? H approaches 0, 2 points become 1, right? What's different about this picture? What did it have? What was this yesterday? With this A? What was this one? A plus. Right. That's it. That's the only thing that's different. Right? So here's what we were doing. So what's the difference? They're just different letters, right? Well, here's the difference. A is a specific x coordinate, right? So yesterday we found f prime of 2, f prime of 3, f prime of 4, right? So like on number 44, we found f prime of 4.
What if I just said, now do f prime of 3? Well, you had to do all over again, right? What if I said f prime of 2? You have to do all over again, right? It would look very much the same, but it'd be different. It'd come out different, right? Because you're finding the slope at different points. What if we could do this same thing and find f prime of x? That is, what if we could find an equation for f prime, right? And then if we wanted f prime of 4, we just plug a 4 into that. If we want f prime of 3, then we just plug a 3 into that. If we find f prime of 2, we just plug, right? If we could find an equation for the derivative, right? Instead of just finding the slope at 4 or at 2 and have to do it every time, that would be really powerful. So that's what we're going to do right now. Instead of saying, okay, here's a function, let's find f prime of 4, let's find f prime of 2, and putting a 2 in for a and a 4 in for a, we're just going to put an x in for a. So we're going to do exactly the same thing here. So we're going to start out with our f notation, so it would be f of what? X plus h. So we're taking this same definition and we're just taking the a out and putting x in its place instead of putting a 2 in or a 4 in. Minus f of x all over h. Right? Okay? Now, all that is just the slope. It's subtracting these two, subtracting the y's, subtracting the x's, right? It's the same exact thing. All right, now to be honest, this is the version of the definition of derivative we're going to memorize all year long. We'll actually, because think about it. If I have this, and then I tell you I want you to do f prime of 2, well, that just says put a 2 where the x was. So you put a 2 there, you put a 2 there. Instead of saying put a 2 where the a was, right? Same thing. Same thing, right? So they really are the same. But when I work this out, I'm not just going to get a number answer, as you're going to see. Watch what happens. Watch what happens. Okay, so now here we go. Today you see me use some color. So let's do that. What's that mean? What's f of x plus h mean? Put an x plus h in for x here, right? So we're going to get x plus h squared. Minus, and then what's f of x? That was the green thing I think I had. So this is blue, this is the blue, and then the green would be what? F of x, oh, it's just x squared. Yeah, f of x is put an x in for x, right? It's just x squared. Okay, x squared. All right, all over 8. So that looks just like what we've been doing. Okay, I should be putting this limit as h approaches 0. Okay, so what's x plus h squared? Foil it out. What do you get? X squared plus 2xh plus h squared minus x squared all over h, which equals, now the x squareds cancel, so we get 2xh plus h squared all over h. Let me come down here, so limit h approaches 0. Now what can I do with that? I can take out a h. I get 2x plus h all over h. The h is canceled just like before. And that allows me to do what then? Now I can let h be 0. And what do we get? So what we just said there, and I'll use our new notation, we just said that the derivative of x squared is 2x. So now, what's f prime of 2? What's f prime of 4? We can find the derivative at any point. We just found the derivative of x squared. Okay? Quickly here. Let's do x cubed. I don't know how quickly it'll be. But this part will be the same. F of x plus h. Again, I always like writing out the f notation. And I know I'm going fast here, so let me slow down a second. Now we just did an x cubed earlier, right? We just did x cubed at 4, right? And what did we get? Wasn't that the one we got 48? Wasn't that problem number 43? We did x cubed at 4. And that's when we talked about Pascal's triangle.
So we're gonna use that Pascal's triangle trick to help us out a little bit. I'm not gonna make you go past x to the third, okay? So you could FOIL it out if you had to. So what is that gonna be? So we're gonna plug an x plus h in for, right? We're gonna plug an x plus h in for x, so it's gonna be x plus h cubed minus x cubed all over h. Okay, so that's gonna be, next line, so what's x plus h cubed? X cubed plus, don't forget Pascal's triangle. 1, 3, 3, 1 is this row. So it's going to be 3 x squared h plus 3 xh squared plus h cubed, right? So 1, 3, 3, 1. Okay, and then minus all over h. What happens? X cubes cancel. Just for the sake of time here, we'll shortcut a little bit. And then, so what's that leave us? Can we take an h out now? We can take an h out, and that leaves us what?
Can you add that? Oh, never mind.
We're taking out an h, so that's going to be 3x squared plus 3x h plus h squared all over h. Boom. Now we can, now it's okay to put a 0 in for h, right? Now it's okay to put a 0 in for h. And what do we get?
3x squared.
So we just learned that the derivative of x cubed is 3x squared. Now, there can be no question, though, that that came from slope, right? This is why we do the definition right here. Because this is slope, right? It came from slope. And I know you guys are seeing it, right? You're seeing it. So if I now said to you, let's do x to the fourth, that'd be long. Well, you know what the answer is going to be. What's it going to be?
4x cubed.
That's what the answer is going to come out to be. Your calculator actually will do these. If you go to right next to the 9 right here. Now, I know you're not going to use this that often because most of the time this is going to be no calculator kind of thing. But see this notation, see this right here, see this button right here, that Leibniz notation right there? See that? Okay. Put an X there. Put an X to the fourth right there. And enter. Now earlier we did this at 4, right? Put a 4 in there. 48. 4 squared, 16. 16 times 6 is 48. Right? What we have is a rule. What we have here is a formula for the derivative. We can find f prime. All right, so in your notes, if we had to summarize this as a rule, which it is called the power rule, if you have x raised to any power, now look what we've already learned. We did x squared and it came out to be 2x. We had x cubed and it came out to be 3x squared. We had x to the fourth and it came out to be 4x cubed, we just did on the calculator. What if we had plain old x? What would that come out to be? Would it just be 1? Because wouldn't it be 1x to the 0 and what's x to the 0? 1. But now think about it. F prime is slope, right? What's the slope of y equals x? It's always 1, right? So what do you suppose the derivative of 5x is going to be? 5. And 7x is going to be 7. Right? Makes sense. We would have known that before we ever did any of this, right? Matter of fact, Emily, that's a problem you were doing in the beginning of the review. I'm not sure everybody did it because it wasn't one of the bold ones, right? But we talked about that. If you have the function 5x, the slope is always 5, no matter where you are, right? Because it's a constant slope. Okay, so you're right, it would be 1. But we could put maybe kind of invisibly here a little bit. I'm trying to do a dotted line. Okay. X to the 0, you wouldn't write it, but it would be. Okay, so what's the rule? So let's finish it. So if you have x raised to the power n, what's the derivative of that? N times x to the n minus 1. So what we're saying is you're going to bring that power down in front. So it's x to the 4th. We're going to bring that power down in front, and we're going to drop the power by 1. And that is one of the coolest rules that there ever is.
So if your x equation has a coefficient, is that just messing with the rule?
Okay, let's talk about that. Okay, I'm glad you asked that. Okay, because we got this right here. Okay? All right. Oh, wait, leave your hat on. Leave the hat on. Okay, so tell me if it's, did it restart? Probably has to reconnect here. How about now?
Oh, yeah.
Is it going? Okay, you can take the hat off now. All right, thanks. All right, so what happens if you have a coefficient in front? So let's talk about that for a minute. So if you have 4x to the 5th, don't look at this counter now. This is supposed to be a surprise. It's supposed to be a surprise, second block. I don't want you sneaking a peek here. All right, 4x to the 5th. So if you got a 4 out in front, what does that do? Does it mess it up? Well, let's talk about what that does. What did a 4 in front of a function do? Stretched it this way. What do you suppose that does to slopes? By a factor of, don't you think it'll make the slopes bigger by a 4? So don't you think the f prime equation would also need to have a 4 in front of it to make the slopes 4 times as big? Sure enough, it does. So you would bring this 5 down in front, and it would be 20 x to the 4th. So if you have a coefficient out in front, it will just stay there. So that 5 will come down, multiply by the 4. Yes, because of that stretching, it makes sense. That's what it should do. Okay, all right, so we've got some of those. I want to make a little table just talking about some of those right here. Okay, so we've got some f functions with powers, and we've also got sine in there because we've learned that one about cosine. So we've got 2 basic rules. We know derivative sine is cosine x, so we got e to the x as its own derivative, and then we've got now this new thing called the power rule. I call it a shortcut sometimes, right? It's a lot faster than going through the long way, but anytime, including on the quiz next week, it says use the definition of the derivative, they're talking about doing it the long way, right? With the definition. Okay, what about this one? Well, what's that minus 4 do? 4 to the right. Does it change any of the slopes? No, but it changes where they are, right? All of those slopes that were on this graph are now shifted over 4 to the right. So doesn't it make sense the x minus 4 ought to stay there in the derivative? It does. So one of the rules you're going to learn when we do these derivatives is there's stuff on the inside, you always leave the inside alone. The inside will always stay there. So right here, what you're going to do is bring down to 5. You're going to leave that inside alone, and then you're going to drop that power by 1. So again, you're going to use the power rule, but if there's stuff on the inside, you're always going to leave that stuff on the inside. All right, here's the tricky. Here's the tricky one right here. What did a 3 on the inside do? Compressed it. Does that change the slopes? Yes. It's making them what? Steeper, right? So if you shrink them, if you compress by a factor of 3, they're going to get steeper by 3. So you're going to need to multiply, and not only that, but if you compress them, this slope that was here is now been moved in as well. So the new graph, the f prime, will be compressed and it will be steeper. You see what I mean? Both of those. So we have to leave the 3 on the inside because of the compression, and we have to kick out a 3 on the outside because the slopes are 3 times as much. So here's another rule. When you have a multiplier on the inside, you leave it on the inside, but you have to kick out that multiplier to the outside as well. When you have a multiplier on the, so we're going to bring the 6 down. We're going to leave the 3x on the inside. We're going to drop that to a 5 because that's what the power rule says to do. We're leaving the 3 on the inside because it's compressing where those slopes are, and we have to kick out a 3 multiplier because those slopes are all going to be 3 times as steep as they normally would be. Now we should simplify that then, put the 6 and 3 together, and then we leave it like that. So that's a tricky one. You've got a multiplier on the inside of a function. You leave it on the inside when you do the rule, and you have to kick out that multiplier as well. Same thing if that would have been a 1/3. If that's a 1/3 in there, that would stretch it. Well, that would make the slopes not as steep. So you'd multiply by 1/3, which would make them not as steep. Okay? All right, so what about sine? What's the normal rule for the derivative of sine? It's cosine. And like we just said, we leave the inside alone because that 2 compresses the graph. So we have to leave the compression there because all those slopes are now moved in. And we have to kick out a 2 because since you're compressing it, you're making it steeper by a 2 factor. So you need a 2 kicked out side as well. Now I could have put it on the right side, but usually then we just move it around to the front anyway. Kind of like this 3. I kicked it out here, but I just usually move it back around to the front. Okay? All right. So what about this one? This 3 on the outside. What do we say if there's something on the outside? Just leave it, and then just do your normal rule. So the derivative of sine is cosine, and the 3 just stays on the side. Because remember, that 3 was a stretch. That 3 was a stretch, so it makes all the slopes 3 times as much because you're stretching it, but they don't move anywhere. They're just stretched. So you need a 3 on the outside of that as well, so it just stays there. So a number multiplied on the outside just hangs out there. Okay? Now, what we say x, the derivative of x was? 1, and then that 7 is just going to hang out there, so that's 7. Or think of it like a line that's 7x. What's its slope? It's always 7. So what you'll quickly learn is anytime you're doing a derivative of plain old x, x to the first, whatever number's in front, that's the derivative. So 7x, derivative is 7. 8x, derivative is 8. 9x, derivative is 9. What's the derivative of 5? Because wouldn't that be a horizontal line? What's the slope of a horizontal line? 0. So the derivative of any constant is always going to be 0. Now the other way to think of it is this. Think of 5 as 5x to the 0. Bring the 0 down in front. What happens? Wipes it out, right? So bring the 0 down in front. 0 times whatever is going to be 0. Okay, so you can think of it that way, or you can just think of it, okay, y equals 5 is just going to be a constant. And the derivative of that is just going to be 0. Horizontal line. Derivative is always 0. So a constant derivative of that is always going to be 0. Okay, let's do a couple more. Okay, what if you have some weird powers? Like a negative. What's another way to write 1 over x cubed? See, because here's what some people might think. See, some people are going to look at this and think, oh, that'll just be 1 over 3x squared, like that. I'll just do the power rule on x cubed. No. That's not what the rule says. The rule says when you have x raised to a power, not 1 over x to a power. That's not what the rule says. So 1 over x cubed is the same as x to the negative 3. Now you can do the power rule. So it becomes negative 3 x to the negative 4. Remember, you got to subtract 1. So -3 subtract 1 is -4, not -2, right? You gotta make sure you do that. Now, I'm okay with you leaving it like that. If you wanted to drop that down to here, sometimes that might be useful in a problem, but I would say most of the time I would just leave it like that. What's square root of x? That's x to the 1/2. So the power rule works on that also. So what would the derivative be? 1/2 x to the -1/2. Remember, you got to subtract 1. So it's 1/2 take away 1, or 1/2 take away 2/2, which would be -1/2. So we're going to have to be able to work with fractions. Okay? What about this root? What is that? That's x to the, it's 4/3. Remember, the root is always the denominator. The root is always a denominator. So cube root is going to be a 3 on the bottom. So what's the derivative of that? 4/3 x to the 1/3, because that'd be 4/3 take away 3/3. So that'd be 1/3. Okay? All right, what happens if you have a string of terms together? Well, there is a rule with these that it's okay to just do their individual derivatives. If you have a string of terms, you can do the individual derivative of each term. So this would, yes. So this would be, bring the 4 down, so it would be 12x to the 3rd minus 6x squared plus 0. We usually wouldn't write the 0, but we'll write it here just to make the point. Okay? Now, what happens if you got a couple things multiplied? It seems like here, when they're added and subtracted here, we just did their individual derivatives. Now, if you thought that's what you would do, don't write this down. Some people might think, oh, just do 3x squared, and then do 4x cubed, and then put those together, and that would be 12x to the 5th. Would you agree? Right? But it turns out that's not right, because what's x to the 3rd times x to the 4th? That's x to the 7th. And what's the derivative of x to the 7th? 7x to the 6. Is that 12x to the 5th? No. So, we just learned an important thing there. If you have two functions multiplied together, you can't just do their individual derivatives. We're going to have a special rule for that. Okay, and so last one. So, because of what we just learned, it would be real tempting to think that the derivative of this is 3x squared times cosine. It'd be real tempting. It is not. So I'm just going to put a question mark by that for right now, and we will come to that in chapter 3. Okay? You can put it in your calculator if you're really curious. But in chapter 3, we will learn about that one. But we cannot just do the derivative of that, because we just saw in that previous one, when they're multiplied, you can't just do their individual derivatives. Doesn't work. But when you're adding a bunch of terms together, if this would have been x cubed plus sine x, then we're good. We could do x cubed plus, the derivative of sine, and we have it. All right. So that is the end. So you've got your homework is the 2.2 homework. Let me see. And this, this is not real tough, because it's going to have some stuff where you're just doing, some of it you're going to be doing by the definition, but a lot of it's going to be kind of the shortcuts now that we've learned the shortcuts. So you're going to get to do some of these shortcuts with some of them. It's not too bad. But notice on the assignment sheet, it says 2.2, and then it says do 1 over x and square root of x by the definition. Okay, you need to work those out by the definition, and I'm going to really be checking your work on that when I go around and look tomorrow. Okay, I want to see the effort you put in now. What?
Is that the definition?
That's the definition. Yeah. So in other words, it looks like this. In other words, it's going to look like this, how we did x cubed, right? Except you're going to do it for 1 over x. So guess what? You're going to need the bow tie. And then square root of x, guess what you're going to need? The conjugate. You're going to need the conjugate. Okay, so right here, when you set this one up by the definition, you're going to need bow tie. And when you do this one, you're going to use the conjugate. Okay, you're gonna need that. All right, to work those out by the definition. Now we know what they should be. I mean, square root of x we already did, right? Square root of x we did right here. We know we should end up with this when we're done, right? Now that we know these shortcuts, we know what we should end up with. And then this one is just x to the negative 1, right? X to the negative 1, and we can do the shortcut, so we know what we should end up with, right? But I want you to go through and practice that algebra on those by doing it by the definition. Okay? All right. So, sorry, apologize for not a lot of